Hi, my name is Hatem Ltaief. I'm a senior research scientist working at the Extreme Computing Research Center at KAUST. I'd like to give you a status report from Saudi Arabia in the context of the ISC 20 HPC Asia workshop. Saudi Arabia has 3 top 500 listed computers from the last list released in November 2019. All these supercomputers are purely CPU based. Shaheen 2, a Cray XC40 system hosted at KAUST, and 2 other supercomputers, Machman 3 and Machman 2, operated by Saudi Aramco, primarily for exploration and exploitation. Saudi Aramco is organizationally and fiscally distinct from KAUST, but relations are close. KAUST and Saudi Aramco pursue their supercomputing objectives in a mutually coordinated manner. Saudi Aramco was the founding organization for KAUST. Saudi Aramco has hired close to 400 KAUST graduates into its research programs. We have several joint milestones: a full-scale 100 Hertz inversion simulation, a trillion cell reservoir simulation, and a 200,000 core oil gas separation done via ANSYS commercial package. Besides Saudi Aramco, KAUST has several industrial partners, including SABIC, Dow, Boeing, and IBM. We have a newcomer from the region to the top 500 list, from UAE. They put together 2 systems, and in particular, the one ranked 26, Artemis, is purely based on GPUs. It's hosted by Group 42, which is an Abu Dhabi-based artificial intelligence and cloud computing company that develops and deploys AI solutions. The performance reached by Artemis is almost 10 petaflop. Some of our HPC efforts at KAUST are driven by our in-house applications: computational chemistry, seismic imaging, climate weather prediction, and combustion. To sustain the performance of this application on emerging technology, we need to constantly revisit the core algorithms and their corresponding implementations. At ECRC, we have been designing and implementing several layers of the traditional numerical software toolchain. The Multiple Object Adaptive Optics, MOAO, software framework provides HPC real-time controller to compensate for atmospheric turbulences. It's being deployed on the Subaru Japanese telescope in Hawaii. The ExaGeostat, a software framework for geospatial statistics for climate weather prediction, which provide an R interface for end users. KBLAS, an HPC implementation of a subset of BLAS kernel on CPUs and GPUs. It has been integrated twice into NVIDIA cuBLAS library. KSVD, a distributed memory singular value decomposition solver, which has been integrated into Cray numerical library LibSci. GERI, an HPC stencil computation based on multi-core wavefront diamond tiling using temporal blocking. And last but not least, HECMA, a data sparse linear solvers that received best paper at ISC 20 for simulating acoustic wave scattering application. KAUST has deployed a Cray CS Storm cluster of nearly 500 nodes composed of NVIDIA GPUs. This is all in the context of the strategic AI initiative at KAUST. We have an increased demand to support AI workloads in genomics, video processing, pattern recognition. Is AI HPC or is HPC AI? We believe that AI and HPC have actually sufficient overlaps, and it is possible to support both workloads using a single system. And that's all what is Shaheen 3 all about: finding the right alchemy to support a broad set of HPC and AI applications. The current plan is to have the new system operational by 2022. Like in many other research institutions, KAUST has put together a rapid research response team for fighting COVID-19 pandemic. The supercomputing lab has allocated 15% of its annual resource allocation budget. This is 225 million core hours. In particular, I'd like to highlight the work by Professor Arnab Payne. One of Professor Payne's projects is to provide a comparative genomic study of SARS-CoV-2 genomes. The idea is to find out the global genetic signatures of the SARS-CoV-2 virus. The team has investigated the nucleotide variation landscape of a large set of globally derived SARS-CoV-2 genomes and defined major mutation events. Currently, the number of available viral genomes has risen to over 23,000, and hence it requires access to major computing facilities for tracking the mutations in the virus genomes and update the genome variation barcode on a regular basis. 37 gene clusters are shown with a binary heat map representing presence in black or absence in white. We can see that SARS-CoV-2 virus has some resemblance with previous SARS virus. One could perhaps identify existing drugs to fight the current pandemic from that result. At the same time, one of the gene cluster of 2 here, marked in yellow, is a case of annotation artifact, as it appears to be unique in SARS-CoV-2 according to annotation from GenBank. This gene is not predicted in any other genomes. This study is very interesting. In the ECRC, we have provided the 3D unstructured mesh of the SARS-CoV-2 virus using its molecular structure extracted from the protein data bank. First, we have meshed the spike protein, which is the key of SARS-CoV-2 for entering and infecting human cell. Then we stitch many of those S proteins, around 80 of them, to the sphere body of a single virus. We have then created the mesh of an entire population of viruses. The main idea is to study the various interaction with their deformations during their transport in a droplet or in the upper respiratory tract and simulate the multiscale mesh deformation. We design and implement a high-performance software framework that calculates the mesh deformation of 3D moving bodies using the radial basis RBF interpolation technique. Our simulation, or a framework simulation, takes advantage of the data sparsity of the symmetric positive definite matrix operator by 1, performing lower rank approximation of its off-diagonal tiles, and 2, using a Cholesky-based solver on the tile low rank compression data format. Exploiting the rank structured property of the matrix reduces the arithmetic complexity as well as the memory footprint and allows solving large 3D mesh deformation problems otherwise intractable. This heat map 3x3 matrix shows the rank distribution of the RBF matrix resulting from a single virus with 10K mesh points. Each row represents the 3 truncation threshold. Each column shows the ordering technique. Ordering technique helps in reducing large ranks, while the decrease in truncation threshold increases the ranks. The resulting RBF matrix has evidently a data sparse property that we intend to exploit. This graph shows the performance in seconds of data sparse HECMA solver against dense dplasma solver on Shaheen 2 for simulating the mesh deformation of a small population of viruses with cross interactions within a respiratory tract. HECMA outperforms dplasma by an order of magnitude and can solve problems with much larger mesh points. This graph illustrates the performance of the HECMA solver inside the droplet. The figure reports the time to solution to compute the mesh deformation of almost 1 million SARS-CoV-2 viruses on 2 different distributed memory systems. This scenario translates into a simulation with 10 billion mesh points. Our HECMA solver provides weak scalability as we increase the number of viruses and the number of nodes. Some takeaway: we have introduced a versatile multi-scale simulation framework for computing unstructured mesh deformation of 3 bodies using the RBF interpolation. We simulate the transport of the SARS-CoV-2 virus within a droplet and inside the upper respiratory tract. We achieve up to 2 orders of magnitude against state-of-the-art dense solvers. We provide a tool in the software toolchain to better understand the propagation of the virus. We plan to explore aspects of the binding of the S protein of the ACE2 human protein that are influenced by fluid dynamical interactions before molecular dynamic model and simulation take over. Thank you for listening.